Good morning, everyone. My name is Dushyant Gopal, and along with my co-author, Mr. Vaishak R, I am presenting our work titled Gait-based user authentication system using machine learning on mobile devices. This research was carried out at Srinivas University here in Karnataka, Mangalore, India, and I'm honored to present it at the IEEE International Conference in Malaysia, IICAIET 2025. So, without any further ado, let's begin with our presentation. Smartphones today are the primary gateways to highly sensitive data and services. Protecting user access is a fundamental security requirement. Conventional methods like passwords and pins are vulnerable to social engineering, brute force, and shoulder surfing. Biometrics such as fingerprint and facial recognition improve convenience, but they also suffer from spoofing attacks, environmental sensitivity, and privacy concerns. This motivated us to explore gate-based authentication, which is a behavioral biometric that is unique, unobtrusive, and can operate continuously in the background. The matrix below, figure 1, contrasts common modalities. Passwords need no hardware, but a higher user effort and are prone to phishing or guessing. Face and fingerprint are convenient but require hardware and are sensitive to environment or skin conditions. Both carry biometric privacy considerations. Uses built-in sensors, enables continuous passive checks with no extra user effort, and with on-device processing keeps privacy risks lower than server-side biometrics. Now let's look at the research context. Prior studies have shown that gait patterns can be captured unobtrusively using mobile sensors such as accelerometers and gyroscopes. Early work used distance metrics like dynamic time warping, which lacked robustness. Later, CNNs and RNNs achieved better performance, but they often required high computation and controlled environments. So the gap lies in building a system that is lightweight, robust in real-world conditions, and privacy preserving on mobile devices. Historically, gait recognition started with DTW, dynamic time warping. You can see in the figure 2, which worked for small datasets but wasn't robust. Around 2013, CNN-based methods improved feature learning but were limited in temporal modeling. Later, CNN combined with RNN hybrids appeared better at sequence modeling but still computationally heavy. Our work advances this by using a hybrid CNN BiLSTM which balances accuracy, efficiency, and real-time feasibility on mobile devices. Now let's look at the contributions of our work. Our contribution is to design an end-to-end gate authentication pipeline specifically for smartphones. We developed a hybrid CNN and BiLSTM model that extracts deep features and captures temporal dependencies in Gait. Importantly, all computation is performed on the device itself, ensuring privacy and compliance with regulations like GDPR. The system achieved an accuracy of 94.3% with very low false acceptance and rejection rates, making it a strong candidate for mobile security. The novelty of our work lies in three pillars: a lightweight model that runs on device, real-time feasibility with millisecond latency, and privacy preserving design with no raw biometric data leaves the phone. Together, this makes our system uniquely suited for secure mobile authentication. So our hypothesis is that human gait signatures can be reliably captured on by mobile sensors and used for secure real-time authentication. To validate this, we set three objectives. First is to design a lightweight hybrid deep learning model combining CNN and BiLSTM. Second is to ensure robustness across device positions and environmental conditions. And third, to prioritize user privacy by keeping all processing local to the device. Our objective is to balance three critical aspects in gate-based authentication: accuracy, ensuring reliable user identification; privacy by keeping sensitive data on device; and real-time performance. With sub 20 millisecond latency, the proposed hybrid CNN and BiLSTM sits at the intersection of these three requirements, addressing them simultaneously, which is prior methods often failed. The system architecture is a modular uh, and consisting of five stages. First, the smartphone sensors, accelerometer and gyroscope, capture gate data at 100 Hz per second. Second, pre-processing, filters noise and transforms readings into Earth coordinate frame. Third, we extract features, temporal side metrics, frequency features via wavelets, and deep CNN features. Fourth, classification is performed by a CNN followed by a BiLSTM to capture both local and sequential patterns. Finally, an adaptive decision logic applies thresholds based on user history and context to produce the final authentication decision. The system workflow diagram you can see in the slide. In our experiments, the proposed model achieved 94.3% accuracy, significantly outperforming a baseline SVM model, which reached only 82.7%. The false acceptance rate was just 2.1%, while the false rejection rate was 3.6%, leading to an actual error rate of 2.8%. We also tested robustness across different device positions. The system best the system performed best in handheld mode at 95.1% accuracy, slightly lower in the front pocket, and understandably lowest in the backpack at 89.2%. These findings confirm that our model is both accurate and practical for everyday use. You can refer to the bar chart for clarity. Our proposed CNN plus BiLSTM system significantly outperforms the SVM baseline across all metrics. As we have told earlier, we achieved 94.3% accuracy versus 82.7% for SVM. More importantly, the false acceptance and rejection rates are much lower, and the equal error rate is reduced from 8.3 to only 2.8%. This chart makes it clear that our system offers both accuracy and robustness, which is critical for authentication. If you look at the figure 6, the chart 6, we validated how device placements affect authentication accuracy. When the phone was handheld, accuracy was highest about 95.1%. This is expected since handheld usage produces stronger and more consistent motion signals. In the front pocket, performance remains strong around 93.7%, showing the model adapts well even when the sensor orientation changes. In the backpack, accuracy drops slightly to 89.2%, mainly because the signal gets damped and the gate dynamics are less distinct when the phone is not close to the body. The key takeaway is that our system remains robust across common carrying positions, consistently above 89% accuracy, which is sufficient for real-world mobile authentication. Let's look at the results and validation. Latency is critical for user experience. Our system had an average decision latency of 18.2 milliseconds, which is fast enough for real-time mobile applications. We also validated security against different threats. In mimicry attack, untrained imposters had little success, while trained imitators still struggled to bypass the system. Spoofing with artificial signals was detected through plausibility checks and sensor fingerprinting. Even adversarial ML attacks were mitigated using input reconstruction and gradient masking. Additionally, all processing is on device and privacy is enforced using anonymization and differential privacy measures. We evaluated the security of our system against three types of attacks: mimicry, spoofing, and adversarial ML. In mimicry, as I have told earlier, skilled imposters could sometimes succeed with a 12% success rate, but is still far below normal threshold. Untrained imposters had only 3% of success rate. You can see the figure 7, which shows how the different attacks and their success rates and how they perform after the defensive strategies have been imposed. Our results demonstrate that gate biometrics are a viable alternative or complement to existing authentication methods. Compared to face recognition, Gait requires no additional hardware and works even in low light conditions. Compared to fingerprints, it enables continuous touchless authentication and is more resistant to spoofing. These qualities make it especially well suited for mobile environments where seamless, non-intrusive, and privacy-preserving security is increasingly important. All the aspects of this comparing to different other authentication system we have seen in before in slide 2. So to conclude, we have presented a secure, efficient, and privacy-aware gate authentication system for mobile devices. Our CNN plus BiLSTM model achieved state-of-the-art accuracy while remaining lightweight enough for real-time deployment. We confirmed robustness across positions, environmental conditions, and various attack vectors. For future work, we aim to optimize energy consumption, integrate federated learning for decentralized training, and conduct longitudinal studies on how gait changes over time. Finally, we sincerely thank all participants and Srinivas University for their support. Thank you for your attention. I'll be happy to take questions now.